So please go ahead.
Thank you very much for the opportunity. Can you hear me well? Yeah? So this is a plot I always show to my students about the difficulty of how to do these kind of calculations. And today, Dean and Benjamin are showing that we can go beyond what I expect from theory. So I want to focus on the experimental side to be as accurate as possible on the experimental side and trying to complement theoretical calculations in a way that we can be certain that we are moving forward. So obviously, as I ask just right now, we have this binomial problem, and you know the size of the model space is just exponential as you go above neon 20, for instance, 10 to the 24, 10 to the, you want to solve it, the Schrodinger equation exactly. And the challenge is to reach the numerical convergence of physical observables in the Hilbert space. And for that, we need an effective interaction defined by a model space. So these chiral effective field theory interactions are very good, but they are not, in my opinion, there are many of them, and they don't converge to get the matrix elements, the overlap between wave functions. They're very good, as Dean mentioned right now, to measure energies, binding energies, but when you try to a more stringent test of theoretical models, they don't perform so well. So this is my personal opinion, of course. This is a part of this clustering that we are talking. This is neon 20 here. This is the quadruple moment I'm going to be talking about, and that was like 40 years ago. You have all these mean field calculations, shell model calculations, and even right now, our initial calculations I will present in this talk. And they cluster around point minus 15 or E Fermi square, and this was the experimental data point, which was off quite substantially. So calculations were not doing very well in those years. And the idea of a nucleus having a linear combination forming a cluster comes from Morinaga originally, where he assumed that there was a linear pattern where you could arrange the different protons and neutrons, and then Ikeda brought up this Ikeda diagram where these actually arrangements of particles, of protons and neutrons, they happen at different energy. So basically, the cluster emerges as a function of excitation energy, and which was kind of the picture that we have for many years until early 2010, 2012, where Thomas Neff and then the group of Elias Kahn and Jean-Paul Lebrun, and then also Benjamin here, they came with the first ground state calculation of neon 20, where you could see a beautiful clustering already in the ground state, which wasn't expected because you have 0 plus states, and the 0 plus states normally they have lots of spherical configurations. So this was a beautiful thing, and you can see that this happened having a relativistic density functional rather than having the typical classical one here, which didn't provide. It was better explained in this picture. You have the relativistic EDF here showing the clustering, and then you have the classical Skirm interaction showing no clustering. Oh, not so clear. And this was something beautiful because now we knew that the cluster was also in the ground state, in the mean field, what we consider mean field, and it didn't have to happen as we go up to the alpha threshold. So this is the first calculation done by Jean-Paul Lebrun in November 2019. It's published in our paper here. This 3D plot is first presented today because the referee didn't like the 3D plot in the paper. So this is the first time that we show these similar calculations for the neon 20, the first excitation. So experimental evidence for clustering have been a problem for many years. You know, we have tried here and there, we have shot everywhere. In principle, neon 20 is one of the best clustering nucleus because the 0 plus states is above, in excitation energy, above the alpha threshold. Is the first one, the only unique cases here. You have the other nuclei, the other self-conjugate nuclei, where the alpha threshold is above the 0 plus excitation, the second 0 plus excitation. And another sign of possible, in this case mostly they are attributed to shape consistence, is the shape mixing, which is given by the E0, the electric monopole strength. And as you can see here, for these self-conjugate nuclei, they have very large values, this rho square, which is linked to the mean square charge radii that also Dean mentioned before for different nuclei, and this is linked to the rho square E naught here, and these large values are sign of mixing of shape configurations, and this is normally associated with shape consistence, and in this case with alpha clustering. But we needed to measure that quadrupole moment more precisely than it was known until now, and I will explain a little bit why. But for that we use Coulomb excitation, and Coulomb excitation is a technique where we don't wake up the monster. We don't know the nuclear force by default, so we try to bombard the nucleus with very light well below the Coulomb barrier, so we don't have any nuclear force involved, and everything is excited, the nucleus is excited through the Coulomb force that we know very well. And we measure quadrupole moments. Here is a second order effect in Coulomb perturbation theory, in Coulomb excitation. And the first one is the transition probability, the B2 value, how you populate from the ground state to the first 2 plus. And this is a reorientation effect of the magnetic substates, which depends on the shape of the nucleus. And as you can see here, you have, because of this positive sign, you have the oblate shape has a larger cross-section than the prolate shape, and the one here in the middle is for a spherical nucleus. And so we have typical experiment which has a silicon detector for particle identification and gamma ray detectors. Very important, as I say, we don't wake up the monster, the nuclear force, and so we have to get the distances between nuclear surfaces at least of 6.5 Fermi, so which limits our population, our cross-section. However, it's very important because once you get the nuclear force into play, then you don't get consistent results. It was in this very nice paper by Ray Spear in Physics Report 1981, where they concluded that at least for light nuclei, you need that separation between nuclear surfaces of 6.5 Fermi. So that's what we did, and for doing these experiments, we developed a new pipeline for measuring matrix elements at Itemba Labs in South Africa. So, as I say, we have the typical silicon detector is the double-sided silicon detector with rings and sectors for double correction. We have an array of multiple, up to 18 Clover detectors we can have through the new GAMCA array. And we do particle gamma coincident measurements at backward angles. And obviously, we reduce the background of the gammas by having the silicon detector. So this is the GAMCA, the Lion, the array that we have built at Itemba Labs. It was commissioned in May 2021. And it's based on the dandelion flower, where you have hundreds of different florets clustered together. So this is the same idea, to have as many detectors as possible clustered together and get the best efficiency and resolution possible. As a proof of principle, we ran this experiment. It's better, as you can see here, to run these experiments that you want to study. For instance, argon-36, which is a nucleus that you may be interested to run here because it has an oblate shape, a very well-defined oblate. So you have a spherical, you have the prolate, or the pinball shape, and then you have the oblate also that you can investigate. I think I suggest that would be a nice thing to do. And you can see here the spectrum. This is the gamma ray spectrum without Doppler correction. You see a little valley with little mountains here, and as you Doppler correct the gamma ray spectrum, the gamma rays coming at 10% the speed of light. The incident beam comes at 10% the speed of light, so it looks very nice, and you have a very nice background subtraction there. And this is the data point that we have here for argon-36, a very large oblate shape, which can be understood by the lower energy or the lower binding for the oblate configuration in a Nielsen diagram. So that was a proof of concept. This goes now for 20 neon, the same thing, a very nice spectrum here. That's the our gamma ray peak. And for the first 2 plus excitation, the decay, and you can see the angular distributions, how they agree nicely with data. And this is basically how we knew that we can get a quadruple moment. However, things are not so easy. So here we have also a double second order effect, which is the giant dipole resonance. Is the, I don't know, you know, this is the first collective mode in nuclei that was discovered in 1945, was predicted by Migdal. 2 years later was discovered in Caltech. So basically you have all these E1 dipole excitations going exciting by virtual excitations this region of the giant dipole resonance, and they can go down and polarize the ground state, or they can go and polarize the first excitation. And for light nuclei, they compete with this reorientation effect, which is the one where we measure the quadruple moment. So as you can see here, that polarizability, creates a torque, and that torque enhances the deformation of the nucleus, and this is a correction that needs to be considered when we do these measurements. And we did that, and for neon 20, you can see here thousands of calculations of all the E1 matrix elements going up to the GDR, all these isovector E1 matrix elements, and going down to the final state, which is the first 2 plus excitation. And these are thousands of them, right? And then these thousands of them, as you can see here, for the ground state, they contribute, they add them together because it's the square of them. But as you can see, for the first 2 plus, these matrix elements, they can have a positive or negative sign. And obviously for the first 2 plus, the negative sign for the matrix elements, they contribute and they interfere destructively, changing the polarizability or lowering the polarizability from the ground state to the first excitation. This is a big thing that we need to consider for these light systems. And you can see here the kappa is how much it deviates the giant dipole resonance versus the polarizability effect, the global effect, which depends on the hydrodynamic model. I'm not mentioning that today. And this is for the ground state, where you have photoabsorption cross sections. But this is what we see for the first 2 plus, and this is the one that we use for our analysis. And we determine here the diagonal matrix elements, which, as you can see, is related to the spectroscopic quadruple moment. In fact, what we measure is the diagonal matrix element, or actually the 2D chi-square surface here. So as you can see now, these are some of the ab initio calculations, which also come to about 0.15 as that cluster that we saw originally. And we have different kind of calculations, and this is the previous measurement at safe distances, and this is the new value for 20 neon, which has a very large quadruple moment, as you can see from that picture once you consider the rotor model right there. And that challenge actually became an opportunity. And by using that same formalism I showed you before for the dipole polarizability, we could explain the universality of our process elemental abundances in our universe as part of the change in the symmetry energy. As you go down in nuclear polarizability, that increases the symmetry energy. And as you can see, remember everyone, the same empirical mass formula, if you increase the symmetry energy, you reduce the binding. So we cannot go so far off into the terra incognita, into that neutron drip line, but the neutron drip line kind of gets thinner in a way that there's only one direct way to create this element. So this is a new calculation that was done right recently by the Chinese group, and they are based on different Scherm type interactions. Before we showed that the Scherm type interaction didn't work out, but if you go beyond Scherm Hartree-Fock now, you can see the clustering structure, and you can see very nice with this particular SAMI interaction, Scherm interaction, which agrees nicely with our data point right there. Obviously, I cannot forget the work done by Dean Lee and his group, where they actually determine a very large quadrupole moment. This is Benjamin's, also, it's about the same, but it's also about the same as that cluster of of calculation that we have a long time ago. So this is a remarkable achievement, I think, to get the clustering, the quadrupole moment with the information of also having a clustering, a bowling pin shape for neon 20. Still, the quadrupole moment doesn't provide any information about the bowling pin shape. It just gives you the elongation of the nucleus, right? So we need to, there's only one way, as it was mentioned briefly by Benjamin before, the Kumar-Klein sum rules of a rotational invariance, where you can actually define the shape of the nucleus in the intrinsic frame, both quadrupole and triaxiality. What we measure, what I showed you before, is just the shape of the nucleus or the charge distribution in the laboratory frame, which is like a fuzzy shape. Only through rotational invariance you can actually get the right shape of the nucleus experimentally in our low energy nuclear physics. And for that you need a bunch of matrix elements, electric, diagonal and transitional matrix elements, and generally you get it for the first two plus, mostly for the ground state, because you need the sum rules of all these matrix elements. As you go higher, you need other matrix elements which are not always available. So it's very difficult to get the rotational invariance going on. But here I'm going to propose a different method where we have tested. We thought we were doing something new by taking a rotating nucleus and rotating about the three axes, assuming rotational flow and a constant moment of inertia as a function of spin. So we get a ratio. This is one of them, a ratio of matrix elements. And you can see this is the theoretical curve and agrees very nicely. The data points, we take basically the experimental matrix elements and we compare with this model. And actually this calculation, this ratio here, although it looks very different to the one by Davidov and Filipov, they're actually the same. They're equally the same. The two models agree with each other from different perspectives, right? But what we can see here, that from these ratios, we only need two matrix elements. And it's not like the rotational invariance or the Kumar-Klein sum rules. We only need two matrix elements. And wherever there is Kumar-Klein sum rules, they agree very nicely with this simpler version of how to extract triaxiality from ratio of matrix elements. This is the way to go, and we have done it. Now we have another paper going for more. What nuclei has been considered vibrational for many years, and in fact they are triaxial. There is no such thing as gamma soft. Forget about it. It's only always stable triaxiality, which depends on the uncertainty obviously depends on the matrix elements, on how accurate they are known. But here, with this model, we get rid of the misconception of nuclear vibrations and gamma soft. That will be my next paper. I hope you're not the referee. So conclusions, three-body problem. We have a three-body problem. First, although Dean and Benjamin, they tried to sell us the story is solved and everything is okay, we have a big problem with E2 matrix elements, with quadrupole moments, with B2 values where we don't really converge, depending. There are many effective field theory interactions. As my friend Kai Hebeler said, the biggest problem with the high order chiral effective field interaction is the rapidly increasing number of new unknown couplings, which need to be fitted somehow. 2n is fine, but 3n is more difficult. We live very exciting times. I didn't mention your work. I wasn't here in the morning, sorry about it. But there's an exciting prospect to measure this clustering and triaxiality directly with light ion collisions. And for that, actually, we need to know very well the initial geometry. And here my point is that we need to do experiments also on the other side, on the low energy side, to determine accurately shape mixing polarizability, because polarizability hasn't been measured. We have determined that theoretically. No one has ever measured the nuclear polar stability of an excitation. For the ground state, there's more information there, but there's also some discrepancies in the recent years. Quadruple moments and traxiality through electric monopole, dipole, and quadruple matrix elements. This is what we do. We try to measure those electric matrix elements through existing programs at the solder decay station, at high solder, where we do the Coulomb excitation, and at the Temba Labs with the new GAMCA array. And I think that's it. I wanted to say this is very important. My student, he went to China, he was doing a postdoc, he passed away this year. He was the first author on this large quadruple deformation in neon 20. Thank you very much.
Thanks, Nico. Thanks for the nice overview. So are there any questions to Nico? Yeah.
So this neon 20, the traxiality, that plot, assume is rigid, right? Do you assume rigid in order to use that formula?
We don't assume it's rigid. We assume the ratio of matrix elements, and the ratio of matrix elements, they give you an uncertainty. So obviously this, I assume is rigid in the sense of these matrix elements giving you, they determine this ratio here, right?
Yeah.
So you get this by interaction, you get you get this by experiment, and you determine this. So this obviously is not rigid per se, because there's nothing rigid in quantum mechanics, but I would call it stable traxiality.
Yeah. But then if you have to consider the fluctuation, you need a much more matrix element, right?
You need to know the fluctuation, you need to go, but you cannot do that. Actually, for this nuclei, it's impossible. It's not.
There's not enough energy levels. Yeah.
There are not enough matrix elements that you can determine experimentally. You have to calculate them. There's no, you see, the process becomes adiabatic. Any inelastic scattering, right, becomes adiabatic as you go to high excitation energies. And these light nuclei, the first excitation is 1.6 MeV in neon 20. You go to oxygen 16, is even worse, right? The next one, the second 2 plus, you need all these matrix elements, but they go to 3, 4 MeV, right? So you cannot do that through Coulomb excitation.
Sure. So your conclusion is 30 degree, around 30 degree.
For neon 20 actually we get 9 degrees. It's almost prolate with a small configuration. It's like 9 degrees. So you have 0 degrees is for prolate. I didn't mention that. 60 degrees is for oplate, and 30 degrees is for triaxial. Actually, triaxial is in between 0 and 60, right? So for neon 20, we get, with the available information, we get about 9, 10 degrees.
Yep.
Thanks, Nico. Great talk. I wanted more insight into why the previous experiments were not so good. Why it took for your yeah.
So the problem is, it's an experimental thing, because in the old days, tandems, they couldn't accelerate neon 20, right? So then everyone forgot about neon 20. These measurements were done in the 70s, some of them, this. And these measurement Nakai, remember we need 6.5 Fermi separation between nuclear surfaces. So they did it very short distances.
But the results are not very different. You measured 23.
The results are actually, that's coincidental, because the thing is that there were another case with magnesium 24 where they ran also a similar experiment, and the same authors, Otto Heuser, in that particular case, he neglected his own experiment and said, okay, we have to go above 6.5 Fermi. So the similar results, but untrustable, unreliable, I would say. So the key here was to run, instead of, as you can see here, Dean, you have the projectile was sulfur, and for the only safe measurement, what we show in this particular case is that this formula here, if you go to higher targets, you could run lead-208 or platinum 194, 196, the reorientation effect is enhanced. You have more sensitivity to the quadruple moment. This is what wasn't done before.
Very quick question.
Because you comment on the triaxial structure and also the gamma soft, the beta soft, because my previous comment about the xenon 129, not about the neon 20.
But this happens, so I have done the analysis for everything. All nuclei in that paper, you can see there's no gamma soft anywhere.
Okay.
According to the model, not like a God here, I can tell you what it is, This is what we have come with, right? If you look at that paper, actually xenon 130, where there's Klein some rules, recently from Coulomb excitation, you see that our model agrees with triaxiality between 20 and 30 degrees for xenon 130.
Okay, it's a good topic also for other discussions. But okay, so that's something, Nico again. Thank you very much.
Thank you so much.